Welcome everyone to lesson 1.5 of Precalculus, which is all about polynomial functions and their complex zeros. So this is going to be a longer lesson, so for my kiddos, I'm going to ask them to view it in two parts, but feel free to watch the whole thing. Let's get started. So if there exists a function p and a number a such that p of a is equal to 0, we got a few different things we can call it. We can call the number a itself a 0 or a root. We can say that p has an x-intercept at the point a comma 0, and we can say that x minus a is a linear factor if a is a real number, so no imaginary parts. Something I'm going to preface now is we're going to do a lot of factoring in the future, in calculus. This is something that you have to be very, very good at and very comfortable with moving forward. So I might show some of my steps. I might not show all of my steps. You just have to be okay with that. And if you have questions, ask me in class, okay? So let's start with question 1. We're going to find all of the zeros of this function. To find a zero of a function, your first goal is going to be to factor it. If you can't factor it, then we'll go to the quadratic formula or another method to try to solve it that way. So we have this function here, and I see that there's an x in every term, so I'm going to factor out an x, and that leaves us with x times x squared minus 2x minus 8. And this is a quadratic that is factorable as well, so I'm going to factor that. So x times x minus 4 and x plus 2 multiply in, so negative 4 and 2 multiply into negative 8, and negative 4 plus 2 is negative 2. So if you have a simple quadratic, that makes it a little bit easier for us. And from here, I can really see that 0, 4, and negative 2 are zeros here. So what I'm going to do is, on this lovely graph on the right, I'm going to put those zeros on my graph. We have a 0 at 0, we have a 0 at 1, 2, 3, 4, and then we have a 0 at negative 2. So that's all it really wanted us to do, but for kicks and giggles, I'm going to draw a rough sketch of what this is going to look like. Now you don't know all the information needed yet in order to draw a rough sketch. Why did I start at the bottom and work my way up? Why is the function behaving the way it is? We'll go over that soon, I promise. But for now, that's good enough as a rough sketch, and that shows us that we are indeed crossing the x-axis at those values. So these are when the function is 0. When this is equal to 0, it's 0 at 0, 4, and negative 2. So if I want to see where it's greater than 0, the only place it's going to happen is in between or outside of my zeros. So if I find where it's 0, I can test a value in between and see where it's greater than or less than 0. So if I have a function like this here, x squared minus 2x minus 3, well, if I can find where that's 0, then I can test values to figure out where it's greater than or equal to 0, like it's asking in this question. So this one would be x minus 3 times x plus 1. So that means that 3 and negative 1 are our two zeros. So what I'm going to do is I like to make a number line or a chart to kind of help me out with this. So I'm going to make a chart, and I'm going to say x is on the top, and I'm going to put h of x on the bottom. So I already know that it's 0 at negative 1, and I know that it's 0 at 3. What I want to know now is what type of sign should I be expecting for numbers less than negative 1? So we can write negative infinity to negative 1, numbers between negative 1 and 3, and then numbers 3 and larger. Remember, all of the numbers in those intervals should have the same sign, so I'm going to pick one to test with. So we'll get out another marker here. I'm going to test with negative 2, 0, and 4, because those are the nicest whole numbers I can use in those categories. So what I'm going to do is I'm physically going to plug in negative 2, 0, and 4 into h and see what happens. And I am going to leave h in its normal form. So I'm going to do h of negative 2, I'm going to do h of 0, and I'm going to do h of 4. So h of negative 2 would be negative 2 squared minus 2 times negative 2 minus 3. Negative 2 squared is a positive 4. Negative 2 times negative 2 is also a positive 4 minus 3. So you have 8 minus 3, that would be 5. 5 is positive, so all of my numbers, or all of my values for h for my x's between negative infinity to 0 should be positive. For 0, well, I get 0 squared minus 2 times 0. Both of those turn into 0 minus 3, so I get negative 3. Everything between negative 1 and 3 has a value that is negative. And then we're going to try out 4. We'll have 4 squared minus 2 times 4 minus 3. 4 squared is 16. Negative 2 times 4 is negative 8 minus 3. 16 minus 8 is 8. Take away 3 is again positive 5. So that is positive. So graphically, what this would look like is we know it's 0 at negative 1 and 3, which means that this function should be something like this. And we want where it's greater than 0. And we can see that nicely. Oh, that did not work out the way I wanted it to. Let's undo that. Try that again. It is greater than 0 here. So what I'm going to do is I'm going to say, on what intervals? Well, the intervals it's greater than 0 would be negative infinity to 1, to negative 1, and we want to include that negative 1. So I'm going to put a brace there. And we also have a 0 at 3, and then everything bigger than 3. So brace 3 infinity. So this is our answer. All right, not that bad. The hardest part right now is factoring. All right, so we have some vocab for us. Let me zoom out so we can see that vocab. So the vocab is called multiplicity. Multiplicity is a big idea that doesn't get a whole lot of time, unfortunately, and we're not going to give it a whole lot of time here as well, although it does come up a couple of times when we deal with polynomials, and it comes up a couple of times when we deal with rationals as well. So multiplicity is the number of times a 0 repeats. So most of the time, zeros have a multiplicity of 1, but weird stuff happens when we have multiplicities of 2, 3, so on and so forth. So the big idea with multiplicities is if you have an odd multiplicity, it's going to go through the x-axis at that 0. So it's either going to be negative before and positive after, or positive before and negative after, one or the other, but it's going to change sign at that 0. An even multiplicity, it's going to touch the x-axis and kind of bounce off. So if it was positive before, it'll hit 0 and then be positive after, or if it's negative before, it'll touch 0 and then be negative after. And the weirdest thing with multiplicities, in my opinion, is when you have a multiplicity that is larger than 2, there's distortion, I'll put that in quotation, there's distortion that happens around that 0. What's going to happen is it's going to get flatter around that 0. So instead of going straight through like you might be used to, like it does here on this graph here, it will distort a little bit. It'll flatten out. So what I have here is I have a nice little example for us of a function f of x is equal to x minus 1 to the second power, x minus 3 to the third power, and x plus 4 to the first power. So what this would mean for us is that we have a multiplicity of 2 at negative 1, a multiplicity of 3 at 3, and a multiplicity of 1 at negative 4. So if we look at these graphs here, we can see that it goes through normally, just crosses at negative 4 because that had a multiplicity of 1. It touches but goes back down. It was negative before and it's going to be negative after at negative 1 because that has an even multiplicity. And at 3, it goes through, so it's negative before and positive after, but it's going to flatten slightly at 3. The larger the multiplicity, the flatter it gets. So, kind of big idea I've kind of already harped on a little bit. So if you have consecutive zeros, a continuous function will have the same sign. So if I have a 0 at 0 and a 0 at 1, everything between 0 and 1 should have the same sign. If I have an odd multiplicity, after that 0, if it was positive before, odd multiplicity should be negative after, or vice versa, negative before, 0, positive after. But if it's an even multiplicity, it'll be positive, 0, positive, or negative, 0, negative. So let's use that to help us save ourselves a little bit of work with this polynomial here. So the first thing I like to do is I like to identify what are my zeros and what are their multiplicities. So I can see very nicely that this is a 0 at 2, this is a 0 at 5, and this is a 0 at -7. The weird one, the oddball out, is 5 because that has a multiplicity of 4. The others have multiplicity of 1. So that means at 5, what happened before 5 and what happens after 5 should have the same sign. So I'm going to make a chart like I did before because we are evaluating, we're finding where this function is less than or equal to 0. Let's make a chart and see what will happen. So we have f of x. Oh no, it's p of x. My bad. So we know we have -7 as 1, 2 as another, extend that, we have 5 as our third, and all of these are 0. Now, for these intervals here, sorry, it's going to take me a little bit to write it down. For these zeros here, or for these intervals here, we know that they're all going to have the same sign because they're between zeros or on the ends, right? So what I'm going to do is I'm going to find what the sign is for any of them. It really doesn't matter. In fact, let's make life a little easy for us and do something simple like 0. So let's find p of 0, which would be in this interval here. So p of 0 would be 0 minus 2 times 0 minus 5 to the 4th power times 0 plus 7. So we get -2 times 5, or -5 to the 4th times 7. That is a number that I'm not really wanting to deal with. I do know that this is negative. A negative to the 4th power would be positive, and this is positive, so it's a negative times a positive times a positive. It should be negative in that interval. Now, what I can do from here is I can use my knowledge of the multiplicities to figure out the rest without having to plug in all of the work, or do all of the work. So this was a multiplicity 1, this was a multiplicity 1, and this was a multiplicity 4. So multiplicity 1 means that the other side should be the opposite. Multiplicity 1, the other side should be the opposite. So this function must have started above, crossed, went below, crossed, went above, and then at 5, it's above, hits 5, and goes back up. And we can tell all of that from the multiplicities and whether they're odd or even. So going back to that big idea that we discussed before, we didn't answer the question though. Remember, the question just asked what are the intervals in which p of x is less than or equal to 0? Well, it's definitely less than or equal to 0 here, right? So we're going to say we want -7 and 2 because it's 0 for both of those, and a lot of people are going to stop. That is because they forget that it's also 0 at 5. So union 5. Or you could put a comma. It really doesn't matter unless your teacher's really particular about notation. This is perfectly fine for me. Again, you have to show your work. Definitely like the chart. The chart helps keep everything organized. But this will definitely save you some time in comparison to how we solved the one all the way up here where we had to plug in something for every single one. We can save ourselves a little bit of time remembering how multiplicities work. So that's why we teach them. The next big idea is the fundamental theorem of algebra. That sounds super important, and that's because it is. For polynomial functions, now this only works for polynomials, if the polynomial has the degree of n, it has exactly n complex zeros, including multiplicities. So if I have a degree 6 polynomials, there are 6 numbers that make the polynomial 0 in the complex realm. Now keep in mind that some of that might be repeated. If I have f of x is equal to x to the 6th power, 0 is going to have more than one multiplicity there. So let's talk about what is a complex number, because that might be a little new, or hopefully it's not completely new and I'm just reminding you of its existence. A complex number is any number that's written in the form of a plus bi, where a and b are real numbers, and I is defined as the square root of -1. Here's another vocab word, and this vocab word is going to be a little bit painful, especially if you're not as familiar with complex numbers. A conjugate is the term used to describe the pairing you need to multiply, which is the multiplier, to a pairing, which would be the multiplicand, to have a product of the difference of squares. The difference of squares is here. It is something plus something times something minus the same something, so the a and b are the same. That for both, you'll have a squared minus b squared. That is the difference of squares. It's a nice, easy rule to factor. So if you don't like factoring, definitely memorize this one. It'll make your life a little easier. But the pairing, the one that's missing, so if I have this one, this would be the conjugate. If I start with the negative, the one with that minus b, then this one would be the conjugate. Why do we use conjugates? We use them for radicals. Keep in mind that I is a radical because it's the square root of -1, because if we multiply two conjugates together, it eliminates the radical. So the example I have here is if I have 3 plus the square root of 2 times 3 minus the square root of 2, that would turn into 9 minus 2, which is 7. No more radicals. Everyone's happy. Why do I need to tell you about conjugates? Well, for polynomials, if we have a complex 0 that is strictly complex, it has an imaginary component, its conjugate will always be a 0 as well. So if I have I as a 0, negative I also has to be a 0 because it's its conjugate. What does that mean graphically? So that's all fine and dandy. That's a lot of words. You might have to pause to get any of that down if you're wanting to. So graphically, zeros are where the graph or the curve crosses the x-axis, right? So typically, you probably are used to the one all the way to the left where we cross twice. We have 2 real zeros, so we have 0 non-real zeros. Degree 2 means we have 2 zeros. One possibility is that we have one distinct 0, but it has a multiplicity of 2, so it touches the x-axis and bounces back up. Or we have where it doesn't even cross the x-axis at all. And if it doesn't cross the x-axis at all, that means it has 0 real zeros and therefore has to have 2 non-real zeros. For our degree 3, we have 3 possibilities, and we're always going to have 1 real 0 because our non-real zeros travel in pairs. So we're either going to have 3 distinct real, 0 non-real, 1 distinct real, 2 non-real, conjugate pair, or we're going to have 2 distinct real with one of them having a multiplicity of 2. And you can continue that chart and make even more complex looking polynomials for degree 4 and then degree 5, but degree 2 and 3 are the ones that are more common, so it's good to have an idea of what that looks like graphically. Here's a really, really hard problem. The degree of a polynomial is 8, so n is equal to 8. That is the total number of zeros. It has real zeros at x equals -10, x equals 5, and x equals 16. X equals 5 has a multiplicity of 2. How many real zeros does the polynomial? I think that's supposed to say non-real, actually. How many non-real zeros does the polynomial have? Yeah, that's Mr. Willie mistake right there. So let's count the number of zeros we have. We have 1 at -10. Because of our multiplicity of 2, we have 2 at 5. And then we have 1 at 16. So we have 4 real zeros. Polynomials, if there's a total of 8, that means we have to add something to it. How many complex zeros are non-real zeros? Let's put that as non-real for us. Well, what plus 4 is 8? Well, there has to be 4 non-real zeros. As simple as it sounds, if this is a test question for me, I really do want you to show me this equation. I want to know that you understand what's being asked of you instead of just putting down a number. Okay? Here's another really, really hard question. You're given a non-real zero of a polynomial. Find another zero. Big idea. Let's go back to our big idea. Our big idea was, for polynomials, complex zeros always come in conjugate pairs. So its conjugate should also be a 0. Well, its conjugate would be -3 minus 6i. So the real term would stay the same, and the complex and the imaginary term would be the opposite sign. Super, super difficult. If you haven't already, I'd like you to try the other one. And I'm going to do it in 3, 2, 1, and I'm finished. Super, super difficult, right? Why are those the solutions? Because their conjugates should also be solutions or zeros. And again, when I multiply together those two conjugates, I'm going to no longer have imaginary components because my polynomial is always going to have real numbers as their coefficients, never imaginary components. Otherwise, it wouldn't be considered a polynomial by definition. All right. So here, if we're given some numerical representations, these charts here, and we want to find the degree of a polynomial, we need to look at the changes. And we're going to keep finding the changes of the changes. It's going to get repetitive, I know, until we get equal changes. So we're going to look at the successive differences, is what that would be called, over equal intervals. So the first thing you got to check, my x's, are they all increasing by the same amount? All of these are increasing by 1. All of these are increasing by 1. So equal intervals, we're good. So if we want to find the degree, we're going to find the difference between all of these f of x values. So here, we're going up by 1, up by 3, up by 5, up by 7, up by 9, up by 11, up by 13. So those are not increasing by the same amount. Let's look at how these increases are increasing. That's plus 2. That's plus 2. That's plus 2. So on and so forth. You notice all of those are the same. That's what we're looking for. What difference was it? It was the second difference. Well, it might help if I could spell it. Let's do it this way. It's a second difference. So if it's the second difference that's the same, this polynomial is quadratic, or degree 2. You need to show the successive differences to get this question right. So I'm telling you, if you see this one on the test and you just say, it's degree 2, all of those are squared versions of the x's, I need you to show me the successive differences. All right, let's look at this one. This one looks crazy. All right, we have -1, -11, -33, -67, -113, -171, and -241. Already, that looks really weird, really random. Let's try it again. -10, -22, -34. This is looking like a pattern to me. Have you picked up what the pattern is? Well, let's do it one more time. and we're getting minus 12 for all of them. So this is the third difference, which means that this is a degree 3 or cubic polynomial. All right. So if you are one of my kids, I'm probably going to ask you to pause here and pick up the video tomorrow. Or if you want to, by all means, you can always push through. I'm going to keep going, and we're going to talk about symmetry now with polynomials. And these symmetries can apply to all functions. So if you notice here, I've got some non-polynomials pictured as well. So even functions are functions that have reflectional symmetry across the y-axis. So if I can fold the function over the y-axis and the two sides would line up perfectly, it is even. Some examples of that are x squared, the absolute value of x, and cosine. Odd functions are where I can take the function and rotate it 180 degrees around the origin and end up with the same function. They would map up together. So an example of that would be x, x cubed, sine x. Now I know that I have some transformations going on here for some of these, but again, as they're drawn, they have those symmetries. So that's what those mean, is they're symmetrical in some sort of way, which allows us to do some cool stuff with it. So the big idea here is that even functions have an analytical property that help us with simplifying and proving things later on. They have the property that f of negative x, if I substitute in a negative x, the resulting function is the exact same as I started with. So if I substitute in a negative x and I end up with the exact same function, same signs and everything, then that function is an even function. Odd, how I would test odd functions, is I would do the exact same test. I would plug in, I would substitute negative x into the function, and if I get the negative version, the opposite version of the function I started with, then that function is odd. So let's show analytically whether these are odd, even, or neither. So there's a key verbiage here, show analytically. Showing analytically means that part of the solution is your steps, is your process. So it is looking for you to use the analytical property to show that they are odd, even, or neither. So what we're going to do is I'm going to substitute in negative x and see what happens. So negative f of negative x is equal to negative x to the 6th power minus 4 times negative x squared. A negative to the 6th power would be positive, and a negative to the 2nd power would also be positive. So I end up with f of negative x is equal to x to the 6th minus 4x, 4x squared, which just so happens to be f of x. So f of negative x is equal to f of x. So this function is even. So see how I write it back into this notation? I bring it right back to the property itself. That is what I'm wanting you to do as well, just to submit that you know what you're talking about. Let's do it with g here. G of negative x is equal to negative 2 times negative x cubed plus 5 times negative x. When I raise a negative to an odd power, it stays negative. So this is equal to 2x cubed minus 5x. Does that look familiar? It should. If I factor out, if I pull out a negative here, then everything would change signs. Does that now look familiar? Again, it should. It is exactly what g is. So g of negative x is equal to negative, and this whole thing here substitutes to be g of x. So g of negative x is equal to negative g of x. This function is odd. Last but not least is h. So h of negative x is equal to 6 times negative x to the fourth minus 2 times negative x. Remember that a negative raised to an even power becomes positive, and a negative times a negative is also a positive. That is not correct. There we go. So if I look at this, it's not the same. So it's not even. Let's try factoring out a negative and seeing what happens. Negative, so it'd be negative 6x to the fourth minus 2x. That is also not h. So because neither of those are h, this is neither. All right. Hopefully not too bad. Ooh. So we zoomed all the way to the top for some reason. All right, let's come back down. All right. So why are we calling these functions even and odd? Why use that for the names of our symmetries? Why not just reflectional and rotational symmetry? Well, it comes from monomial functions. If a monomial function has an odd exponent, then that monomial function has odd symmetry. If the monomial function has an even exponent, it's got even symmetry. So if we look here, whether these functions are even or odd, well, if I substitute in a negative x, it's very easy to see what's going to happen. We're going to get 10x cubed, which is negative 10x cubed. So this one is odd. Now, look at the verbiage here. Look at what the question is asking you. It says state, right? Compared to show analytically. Show analytically has a higher requirement of you than state. State just tells me, is it this or this? It really doesn't need a justification. Showing analytically does, because the show means that your justification is actually part of your answer. So for these, we don't actually have to do the whole property and show off the property because it just says state. So I didn't have to do all of this work. I can just say odd, just like I can for this one and say it's even because 4 is even. Like this one, 6 is even, so this is also even, which makes life a little easier. So please pay attention to what's being asked of you. If you're being asked to show, justify, explain, your work is required and probably has points tied to it on a test, where if you see something like state or like what is, you're really not required to show as much work for it. That is it for lesson 5. I hope that you're feeling good about it. If you have any questions, please make sure that you ask them in class. Otherwise, I look forward to seeing you in the next video.